I'm gonna actually talk loud so this gets recorded. So the question was, can you use the small signal diode model on a large signal problem? Um, that's an interesting question in as much as the purpose of the small signal model is to linearize the nonlinear characteristics of the diode, right? So the large signal diode model, particularly the exponential diode model, is a nonlinear relationship between current and voltage. And the small signal model's purpose is effectively saying, well, if I perturb this system by a small amount at its DC operating point, the tangent line of that exponential curve is going to be approximately linear. So instead of doing a bunch of difficult math, I can just use this normal linear math, just simple algebra, and then add those two results together. So realistically, we are doing kind of a superposition type thing to where we're adding the effects of the large signal and the small signal together and calling that the total response of the system. Um, the small signal response should only be due to the small signal behavior or the perturbation. So I think including the large signal effects in there is going to give you erroneous values. Did that explain things? Okay. We're gonna, if we get around to it, talk about the small signal model for the BJT today, which is why I felt it was necessary to make that distinction. But before we do that, we had last talked about this particular problem where we effectively, let's refresh my memory here. We solved for the output voltage of this system, which we found to be 1.423 volts. And since the output voltage is the same as the collector emitter voltage, we can see that our base emitter voltage is 0.8. So VCE is greater than VBE is greater than 0. So our BJT circuit here is biased such that it is in the forward active region. And then I posed the question to you guys, is there a limitation on the size of the resistor that we can place between our supply voltage of 2 volts and the collector terminal? It's currently at 500 ohms, but is there a limitation to the size of this resistor that will push our device out of the forward active region? And the short answer is very much yes. So let's figure out what value of resistor puts us at the edge of saturation, which then begs the question, well, what is the edge of saturation? Okay. So in a forward active mode of operation for a bipolar junction transistor, we know that our base emitter junction needs to be forward biased and our base collector junction needs to be reverse biased. For saturation mode of operation, our base emitter junction remains forward biased, but now our base collector junction must also be forward biased. So the transition state between forward active mode of operation and the saturation mode of operation is effectively the transition from the base collector junction going from reverse bias to forward bias. So a good way to calculate what's going on at the edge of saturation is to figure out what happens when the base collector junction is unbiased, because that's the transition from a reverse bias state to a forward bias state. So in this circuit, we're going to evaluate it, but we are going to constrain VCE to be equal to VBE, because that is the case where our base collector junction effectively has a 0 volt drop across it. So are we all catching what I'm throwing to this far? Okay. So let's look at this guy here. Let's call this resistor just RC. which is what we're solving for. And we're working under the constraint that VCE must be equal to VBE. So VCE is the same thing as our output voltage because it's measured from the collector terminal to the emitter terminal. So how might we write an expression for VCE in terms of VBE, right? We've already kind of done it right here in a sense, because we know that IC, our collector current, is dependent on VBE. So we could say that actually, hold on, yeah. So VCE is, all right. So VCE would be our 2 volts minus the value of the resistor times our collector current, where our collector current can be written as IS times EXP of VBE over VT. We know that VCE must be equal to VBE, so I can simply change this. And so now putting in numbers, we have 0.8 volts must be equal to 2 volts minus RC. Our IS value was 5 times 10 to the negative 17 amps. EXP of 0.8 volts divided by 0.026 volts, like so. The only unknown quantity is RC. Solving for RC, we would find that a value of 1.041 kiloohms is sufficient to place this circuit at the edge of saturation, meaning any resistor greater than 1.041 ohms is driving our circuit further into saturation mode of operation. So let's take a look at what the consequences of saturation mode operation are. So we know that for a BJT to operate in the saturation mode, both the base emitter junction and the base collector junction must be forward biased. So I'm going to draw our sandwich model here again. So this is my collector region that is doped N-type. Up here is my collector terminal. Here in the middle, I have my base region that is doped P+. Out here to the left, I will put my base terminal. And then down at the bottom, we have our emitter region that is doped N++. Here is my emitter terminal. This voltage source, VBE, must have a positive value for our base emitter junction to be forward biased. And this voltage here, VCB, must be less than 0 in order for this junction to also be forward biased. All right, so with both junctions being forward biased, the barrier potentials at both junctions are reduced, which is going to enable electrons to diffuse from the emitter to the base across the base emitter junction, and electrons will be able to diffuse from the collector to the base across the base collector junction. So using blue for electrons, as we've been doing, we should see something like this. So here are our electrons diffusing from the emitter to the base. And then we're also going to have electrons diffusing from the collector to the base. I've chosen to draw these arrows of significantly different sizes to represent effectively the magnitude of this electron diffusion, right? We know that because the emitter is very heavily doped N+, it has a whole lot of electrons that will be allowed to diffuse across this base emitter junction. Whereas our collector is much more lightly doped. So even though the probability of diffusion is going to be similar, there's going to be less electrons available to diffuse. So we should see this contribution as much smaller. Okay. Let me write here base collector as well. All right. So since the emitter is much more heavily doped, net electron flow will still occur from the emitter to the collector, which will result in a total current that is flowing out of the emitter terminal. So we should still see some emitter current, i.e. like so. Hole diffusion is going to occur from the base to the emitter and from the base into the collector. So we should see some holes diffusing in this direction, other holes diffusing in this direction. The hole diffusion into the collector causes a reduction in the collector current. So let's talk about things here very briefly, right? To put this in contrast with what was going on with our forward active mode of operation. So in forward active mode, our base collector junction was reverse bias, which means these electrons here, which are the minority carriers for this p-type region, got swept across the base collector junction due to the very strong electric field. But we did not see any majority carriers from the p region move into the collector because of the very, very large barrier potential. Now, because this junction is also forward biased, we are seeing that holes are allowed to go from the base into the collector, and that hole movement is going to cause effectively a current flowing up. That is going to be of the opposite direction of the net electron diffusion current. And so we're going to see that our collector current is actually significantly smaller, okay? So we're going to have some collector current, IC, and it will still have a net direction down. But now our collector current will have the following value. So it'll be IS times the exponential of VBE over VT, which is our normal collector current. But we're going to subtract from that ISC, times the exponential of VCB over VT. I'm trying to remember exactly what ISC is, but if I'm not mistaken, it is the reverse bias saturation current density for the base collector junction. Just looking at the math purely here, I think that's what it is, but I didn't write it down in my notes. So this term right here effectively represents the probability of electrons diffusing across the base emitter junction. And then we're subtracting from that total amount of current, the current related to the probability of holes diffusing across the base collector junction. To sustain this increased hole diffusion, the base current has to also increase. So our base terminal is still going to be responsible for supplying the holes that are contributing to recombination in the base region, as well as hole diffusion into the emitter and into the collector. And since we're seeing more holes in this region doing things, we effectively have to supply more holes by our base terminal, which means our base current needs to have increased. So our base current, IB, will be IS over beta times the exponential of VBE over VT, which is nothing more than 1 over beta times our collector current, plus ISC. Sorry, it looks like I missed a negative sign up here, so I apologize for that. ISC EXP negative VCB over VT.
Where was the new negative?
In front of VCB. So for a saturated transistor, our quantity beta is actually going to be lower than what we would see in a forward active transistor. And so we'll now have a parameter. Instead of beta, we're going to call it beta forced, which will be equal to the ratio of the collector current to the base current, sorry, not beta, under saturation mode operation, and this will always be less than or equal to the beta that we would experience in the forward active mode of operation. Right, and the collector current. All right, so since a forward bias junction does not carry a significant amount of current until the forward bias voltage is much greater than our thermal voltage, we are going to get a curve that looks something like this. So this is going to be IC on the vertical axis. And this is going to be VCB on the horizontal axis. And this curve is going to be representative of some fixed value of VBE, right? Because there are 3 parameters that are in play here. Our base emitter voltage, which is effectively saying whether or not the base emitter junction is forward biased or reverse biased, or whether or not our majority charge carriers from the emitter are going to be able to diffuse into the base. And then we're also going to have VCB is going to have some effect telling us whether or not we're in saturation or forward active mode. So we should have something that looks like this. And I'm going to call the value here about negative 0.4 volts. This current is going to be alpha times IE. And now we're going to define effectively our ranges. So when VCB is greater than 0, our device is in the forward active mode. When VCB is exactly equal to 0, we are at the edge of saturation. And if we look at our plot here, you can see that for small negative values of VCB, our current largely remains unchanged. We'll investigate that here in a moment. We're going to call this region where 0 is greater than VCB is greater than negative 0.4 volts or so. Soft saturation. And then when VCB is just less than negative 0.4 volts. We'll call this deep saturation. So from this curve here, and we'll investigate this numerically in a moment with an example plot. Effectively, we can push our device into soft saturation without it having any appreciable effect on our collector and emitter currents. So going from forward active region into soft saturation really isn't a problem in the perspective of amplifier design or anything like that, because the total collector current is going to be roughly the same, which means our small signal parameters, which are largely based on collector current and base emitter voltage and things like that, are going to remain relatively unchanged. It's not until we hit the deep saturation mode of operation where we're going to see that using a BJT as an amplifier is just going to give us utter garbage results. Okay. And this is fairly different than what we're going to see with MOSFET transistors, I think, next week. All right, so our large signal model for saturation mode is going to be extremely similar to the large signal model for a forward active device. So here's our base terminal. Between our base and emitter, we will have a diode across which there is a voltage VBE. Down here at the bottom is our emitter terminal. Over here on the right, once again, we are going to have a dependent current source that can be represented as IS, EXP, VBE over VT, or just as easily beta times IB. Over here is our collector. The only difference is that now that this junction is forward biased, it's no longer, our base collector junction is no longer forward biased. It's no longer going to look, excuse me. Our base collector junction is no longer reverse biased, which means it's no longer going to look like an open circuit. Instead, it's also going to look like a diode, where we're going to have some current that is ISC EXP negative VCB over VT. And then I'll do these in a different color. Here's our base current, IB, our emitter current, IE, and our collector current, IC. All right. So let's run through some examples here. So let's say that I have the following circuit. I have a 2.5 volt supply voltage. RC is 2 kilo ohms. Here's my collector terminal. My emitter terminal. Here's ground. Here's my base voltage, VB. We are told that IS is 6 times 10 to the negative 16 amps. And beta is equal to 100. And we want to know what is VB at the edge of saturation, and then B, what is VB at soft saturation, where I'm going to specifically say that our base collector junction has to be biased with about 200 millivolts. So somewhere in the middle of that soft saturation mode. Yes. 2 kilo ohms. All right, so how might we go about solving this thing? So one way would be to use our large signal models, which I believe I have expressed to you guys that I feel are asinine and useless. So how about we go about solving it without using the large signal model? Because again, I believe it is asinine and useless. So what I'm going to do is I'm effectively just going to write a Kirchhoff's voltage law equation down this right-hand leg. Okay. So effectively, I'm going to say that 2.5 volts is equal to the sum of the voltage drop across the resistor plus VCE, because that's exactly the voltages that I'm going to have going down that right-hand leg, right? So using KVL, I could say, let's look at part A here, that 2.5 volts will be equal to whatever my collector current is times RC plus that voltage VCE, where I'm going to explicitly say that this is our voltage VCE, so we're all catching what I'm throwing. At the edge of saturation, we know that VCE and VBE are literally the same thing. So I could say IC is equal to IS times EXP of VBE over VT. Multiply that by RC and then plus VBE like so. And I've done nothing here except put our equation in terms of things that I know and things that I'm trying to solve for, right? VB at the edge of saturation is going to be the exact same thing as VBE because our emitter is at ground, right? So VB and VBE are the same thing. So I have a simple equation that I can solve using the numerical solver on my calculator or the iterative procedure that I try to avoid because it's long and annoying, right? So plugging numbers in here, I can see that 2.5 volts will be equal to, let's scroll up, 2 kiloohms times 6 times 10 to the negative 16, excuse me. Amps times the exponential of VBE, my variable, divided by 0.26 volts plus VBE. And this can be solved, like I said, using our numerical solver to find that our base emitter voltage comes out to be 728.533 millivolts. So before we move along to part C, or excuse me, part B, does anybody have any problem with this analysis? I know we didn't use the large signal model, but I feel very strongly that you don't need to. Okay. It's literally Kirchhoff's voltage law. That's it. That's all we're doing. Just as a quick aside here, and more of me, not gloating, but pretty damn close to gloating. For those of you that had me for circuits 1, and I kept harping on, hey, you need to make sure that you understand KCL, KVL, and Ohm's law, because there's going to be a point in time where nodal and mesh aren't going to be useful. This is that class. We are never going to use nodal and mesh. Everything we do will be based on KCL, KVL, and Ohm's law, just as a heads up. So if you're not good on the basics yet, you will be by the end of this quarter, or I'll see you in the summer. Yes.
Is there any case where you would have to use a large signal platform or a large signal model?
Not really.
Yeah.
Because if we're electrical engineers and understand KCL and KVL, it's just redrawing this circuit in my opinion, a more complicated form. We're doing the same analysis. It's just literally more difficult looking than this. So for part B, we're effectively going to do the exact same thing, but we now have a constraint that our base collector voltage, VBC, is equal to 200 millivolts. So that voltage, I'm going to represent it here in purple, would be like so. Let's just call this 0.2 volts. And just for the sake of argument, let me explicitly make sure that you're aware the negative polarity terminal goes associated with that node. And I'm going to go ahead and put this voltage here as VBE, because that's still what we're solving for. And now I'm going to do a whole new analysis thing where I do KVL along the left-hand side of the screen. Oh, scary. So I'm literally just doing this path, which will allow me to calculate for VBE when we're in soft saturation without ever having to look at that completely and utterly asinine and useless model that we're supposed to use when we're in saturation mode, because it's completely, utterly, and useless, or utterly useless. So we're going to have 2.5 volts is equal to ICRC minus VBC plus VBE based on our polarities. So plugging in numbers and jumping ahead to where we can express IC in terms of VBE, this is going to look like 2.5 volts is equal to 2 kiloohms times 6 times 10 to the negative 16 amps EXP of VBE over 0.026 volts minus 0.2 volts plus VBE. And we can solve this for VBE. And what we'll find is that we have a VBE of 731.278 millivolts, which means our change in VBE was a whopping 2.745 millivolts. So in soft saturation, it really doesn't change the operating point a whole hell of a lot, right? If VBE only changed by 2.745 millivolts, our collector current isn't going to change by a huge amount. So our goal then when designing circuits to bias amplifiers, and we'll talk about this here in a moment, which is how I'm going to introduce the small signal model, is really to just keep it out of deep saturation. As long as we keep it out of deep saturation, we're doing perfectly okay. All right, let's move along to the small signal model. This is where, in my opinion, things actually get interesting. So we are going to develop our small signal model by introducing perturbations between terminal pairs and measuring what changes occur in our device currents. So effectively, if we introduce a change in VBE, we're going to have something like this. So I'm going to call this voltage source delta VBE. Over here on the right-hand side, I'm going to put a voltage source for VCE, and we are holding this to be constant. And what we should see is that there is going to be some change in our collector current, delta IC, some change in our emitter current, delta IE, and some change in our base current, delta IB, and all of these changes are related to each other. Because we know that the base current is related to the collector current by beta, and the collector current is related to the emitter current by alpha, effectively. So if we can figure out the change in one thing, we can figure out the change in all of them, okay? So we're actually going to look at the model for this really quickly, like the equivalent circuit model, so that we can see what's going on here. So here is my base terminal. Emitter terminal. Collector terminal. Way out here on the right-hand side. And it's just so that I have room to write what I want to write, is our constant collector emitter voltage. And then over here on the left-hand side is going to be our input voltage source, where we will have our large signal VBE as well as our perturbation. So the voltage drop across our diode is what controls the value of our dependent source current there, right? So I would argue that our new current here should be EXP of VBE plus delta VBE divided by VT, which will be represented by our current IC plus delta IC. Our base current here is then IB plus delta IB, where we can express IB and delta IB in terms of IC, and our emitter current here is IE plus delta IE, right? So because we have some perturbation in our base emitter voltage, we should see some perturbation in our collector current, which is then going to cause perturbation in our emitter current and a perturbation in our base current, right? So what I am looking for here on my notes, which I legitimately don't see, that bothers me slightly. is a definition for what's called the transconductance of the device. So let's talk about this briefly while I also Google what the relationship is so that I don't screw it up. Transconductance of BJT. All right, so transconductance is a measure of efficiency in a transistor device. It's effectively quantifying the device's ability to convert an input voltage into an output current. So effectively, how well this VBE here at the input of our device gets transformed into a collector current. And its value depends on the DC operating point of the circuit. So oh, that's as easy as I thought it was. I'll be done. Okay. So if we look at this guy right here, we could express this as IS of EXP VBE over VT times EXP of delta VBE VT. All right. Well, IS EXP of delta VBE over VT is just delta IC, right? The change in our collector current. So we are going to define our transconductance GM as delta IC over delta VBE, which actually simply comes out to be IC divided by our thermal voltage. So using this parameter, our small signal model is now going to look something like this, where here's our base terminal. I'm going to put this as a generic circuit element because I'm not sure what it's going to be just yet, across which we have some voltage delta VBE. Here is our emitter terminal down here. And then here's our transconductance multiplied by that voltage delta VBE. Now, for reasons that are completely beyond me, delta VBE has a special symbol in the small signal model of a BJT. I do not know why, but it is called V pi. Literally do not know why it's called that. So instead of this, where we're dealing with all of these deltas, we'll have something like this. So our goal now is to figure out what this generic circuit element here actually represents in our small signal model, right? Now, should be fairly obvious that if the small signal model, or if this was a diode in the large signal model, now it's going to look like whatever the small signal model of a diode is, which is a resistance, right? So mathematically, we can describe this as the change in our base emitter voltage also causes a change in our base current, right? So delta IB is delta IC over beta, or GM delta VBE over beta. And so we could say that the change in VBE divided by the change in IB will become beta divided by the transconductance, and we call this a resistance R pi. So that our new small signal model, the one that we're going to use the overwhelming majority of the time, is this guy. Now, we're going to use this in a couple of examples today for approximately the next 10 to 15 minutes. In our next class meeting, we're going to talk about current voltage relationships in NPN BJTs. And I'm going to talk to you more formally about the early effect that we discussed when we were going over the physics of how a forward active mode BJT works. This is just a little precursor thing here, but right now, our small signal model is completely independent of any changes in the collector emitter voltage. And the early effect shows us how how our collector current changes in response to a changing collector emitter voltage. And that's also going to have some effect on our small signal model. So we're going to wind up modifying it. So this is what we're going to use when the early effect is negligible or not present, and then we'll use the other model when the early effect is there. And like I said, we'll get into it in more detail on Wednesday. All right, so let's work an example here. Where we have a fairly simple circuit. So I have positive 2-volt supply voltage, a 100 ohm resistor. This is going to be my output voltage as a function of time. And this is going to be effectively my input voltage as a function of time. And let's say that IS is equal to 3 times 10 to the negative 16 amps. Beta is equal to 100, and our input voltage is a DC voltage of 0.8 volts with a 1 cosine omega t millivolt signal superimposed on top of it, such that our goal is to figure out what our output voltage is. So what we are going to do is we are effectively going to split this analysis up into two parts. We're going to do a large signal analysis, and then we're going to do a small signal analysis, and then we're going to add the results of those together, which will be how we handle circuits like this forever in this class. Okay? So in order for us to do our small signal analysis, what pieces of information do we need? Well, our small signal model includes a parameter GM, so we obviously need to figure out what that is. Well, what's GM equal to? Literally go back to your previous page in your notes and tell me because I'm too lazy to do it. I think it was IC over VT, right? So this is IC divided by VT. This IC here is the large signal collector current. Okay, so the large signal collector current establishes what our small signal transconductance is, which is why I'm using capital letters for this guy and lowercase letters for here. So capital letters are for large signal stuff, lowercase letters are for small signal stuff. All right. We're going to need to know what R pi is, but that's just related to beta and GM. So if we can solve for GM, we're effectively good to go. So really the only large signal parameter that we actually need to figure out is what IC is. Do we need to do any real analysis for that at all? No, because we don't really have anything that's messing things up, right? So our large signal IC is just going to be IS times the exponential of VBE, which is a known quantity, over VT, which we're assuming to be 26 millivolts. So that's going to be 3 times 10 to the negative 16 amps times the exponential of 0.8 divided by 0.026. And that comes out to be 6.919 milliamps. While we're at it, so that we have a more accurate picture of what our output voltage is doing, we probably need to figure out what the DC operating point of our output voltage is as well, right? So V out DC is literally just going to be 2 volts minus IC RC, or 2 volts minus 6.919 milliamps times 100 ohms, or 1.308 volts. Just for a sanity check kind of thing here, that 1.308 volts is much, much larger than VBE. So we know that this guy is well into the forward active mode of operation. So we're not even running into the risk of pushing it into deep saturation or anything like that, since this is technically an amplifier circuit because we're perturbing it with some small signal stuff. Oh. All right, so from here, our transconductance IC over VT is 6.919 milliamps divided by 26 millivolts, which comes out to be 266.106 millisiemens. R pi is beta over GM. So 100 divided by 266.106 millisiemens, which comes out to be 375.790 ohms. And now let's use our small signal model to determine what the AC contribution to our output signal is, right? So over here on the left-hand side, we have our signal is 1 millivolts in magnitude. There's literally nothing in here that's going to cause a phase shift, so I'm not going to bother carrying the cosine omega t part through because it doesn't matter, right? There's no capacitors or inductors or anything like that that we have to worry about, so I can throw away the cosine omega t without causing any issues whatsoever. Here's our base. Here's our pi, d pi, gm, v pi, I'm going to draw this terminal further over to the right because this will help me explain something here in a moment. Here's our collector. Here's our 100 ohm resistor. Now, I technically already done it, but I didn't do it with any explanation, so I'm going to explain things here. What should my 2-volt supply voltage look like in a small signal? Yes. So in our small signal analysis, we are going to turn off all of our DC sources, okay? So for every DC voltage source, we're going to replace it with a short circuit. For every DC current source, we're going to replace it with an open circuit. So we turned off our large signal VBE already. So that's why there's 1 millivolts and not 0.8 volts plus this, right? So this short circuit down here is effectively us turning off our large signal VBE. And then we're going to short this leg of the resistor to what's called a small signal ground or an AC ground, because that's us turning off our 2-volt supply. Our output voltage in our original circuit is the voltage measured between the collector terminal and the emitter terminal. And so that's exactly where it's going to be on our small signal model as well. So this is going to be the output voltage for our AC contribution, and it's literally just the voltage drop across the 100 ohm resistor. So we are trying to solve for this quantity. How are we going to do that? So you're correct, Brody, but let's think about it kind of in a step-by-step thing because this is our first time really doing it, okay? So we have established, and I hope we're all on the same page, that the output voltage here is the voltage drop across the 100 ohm resistor. So I would argue that using good old Ohm's law, if we can figure out what current is flowing through the 100 ohm resistor, then we can figure out what our output voltage is. Well, I'll be damned if there isn't a current source in series with our 100 ohm resistor. So our output voltage here, V out subscript AC, should be negative 100 ohms times GMV pi because the current is flowing into the negative polarity terminal, right? So V out subscript AC is going to be negative GM V pi times 100 ohms. Well, very obviously, V pi is just 1 millivolt. And actually, since we know what GM is, we can just put that as a numerical value. 266.106 times 10 to the minus 3 amps per volt times 1 times 10 to the minus 3 volts times 100 ohms. Winds up giving me negative 26.610 millivolts, and then in a different color here, I'm going to say that this is actually negative 26.610 cosine omega t millivolts. Right, putting the cosine omega t bit back in because we threw it away arbitrarily. We might as well just add it back in arbitrarily. All right. So before we move along from this point, which is literally just adding our DC analysis and our AC analysis together to see what's going on, if I were to divide this quantity right here by 1 cosine omega t millivolts, what would I get? Like, what would that represent, I guess? Numerically, it's very obviously negative 26.610. But what does that represent? So this is our small signal output voltage. If we divide it by our small signal input voltage, then we must get our small signal gain, or the transfer function. They're the same thing, right? So our small signal voltage gain is V out AC divided by V in AC, which in this case comes out to be negative 26.610. It also happens to be just negative GM times the resistor that we put between the supply voltage and the collector terminal, negative GM RC. This is an extraordinarily simple version of what's called a common emitter amplifier that we are going to go into much greater detail about for the third portion of this class. But we're sowing the seeds for amplifier analysis right now. Okay. So putting these results together, our output voltage is just going to be 1.308, so that's totally a 6, minus 26.610 cosine whatever omega t is in millivolts. So if we were to plot things, here's V out as a function of time. This would be our 1.308 volts. And we'd see some perturbation around that DC offset that is 26.610 millivolts in amplitude. So yeah, small cosine function on top. But it's 26 times larger than the perturbation on our input signal. So we have achieved amplification. The reason why I'm pointing it out is because one of the most common I guess, misconception type things that I see, is that we forget that this AC signal is actually superimposed on top of the DC operating point of the output. So like most of the amplifiers that we've dealt with to this point are op amps and all that kind of stuff that are based on these, but there's a whole lot of extra work that goes in to where if we put a sinusoidal input signal in, we get a sinusoidal input signal out that's centered on zero. But with a transistor amplifier like this, until we do all kinds of design and signal conditioning and all that kind of stuff, our AC signal is actually going to be superimposed on that DC operating point for our output. And so we're going to have to employ techniques in order to drive that operating point closer to zero so that it gives us the output that we're actually expecting that, or that we're acclimated to have with our current level of experience. All right, that's enough ranting out of me for today. We only have 2 minutes of class left. So, all right, see you guys on Wednesday for more fun stuff. We're getting to the part of this class I really enjoy. Yeah.
Does that mean like the cosine function is like when you're doing that? Like,
yeah, so that 1 millivolt cosine function is the thing that I'm trying to amplify.
you also have it somewhat like where that's like the voltage supply.
So you could think of this as a way to, yeah, so if it were a supply fluctuation, this would be telling you how your output point is changing due to that supply variation. Sure, it's just looking at it from a slightly different perspective. One thing that I want to point, I get this isn't like a huge deal or whatever, but this is technically an approximation. So like while we're putting a pure sinusoid in as the input of what we're trying to amplify, we're not quite going to get a pure sinusoid out because of the nonlinear relationship of our BJT. It's going to be close to where it's going to be almost the 26, but it's really going to be 26 on one side and maybe 28 on the other side. Like it's going to be slightly distorted because the relationship isn't actually linear. Yes.
Are these going to be like, how soon do you upload them?
Whenever my student worker gets around to it. I don't even do it anymore.
Okay,
So-
so I'm not gonna be able to beat any like to watch it in
Yeah.
class. So like,
So-
when do they can-
Yeah, so my best guess would be, so Skylar's gonna upload this one probably tomorrow, and then Wednesdays on Thursday, and then Fridays on the following, Friday and next Mondays on the following Tuesday. That's how she usually does it. She only does them on Tuesdays and Thursdays when I'm in my power class.